Hello everybody, and welcome to our first video on Taylor and Maclaurin series. So I've divided this topic up into two pieces because there's a whole lot of material here. And so in part one, we're going to focus on what are Taylor and Maclaurin series, how do we find them, and how do we figure out some general information about the properties of these series. And then in part two, we'll deal with actually applying Taylor and Maclaurin series to help us solve problems. Okay, so we'll start out with a very important theorem, the power series coefficients theorem. And it says if f has a power series representation, or in other words, expansion at A, that is, if f of x can be written as the sum from n equals 0 to infinity of c sub n times x minus a to the n for all x such that the absolute value of x minus a is less than r, then its coefficients are given by the formula c sub n equals the nth derivative of f evaluated at a divided by n factorial. So we'll take a look at the proof, and this is kind of an informal proof, kind of more of a pattern recognition thing here, but we take a look at the 0th derivative, which is just f of x. And when we evaluate this derivative at a, so when we plug in x equals a, what do we get? This becomes 0, and this becomes 0, and this becomes 0, so forth and so on. And the only term that's left is c naught. So f evaluated at a is c naught. Now, if we take the first derivative, we get c1 plus 2c2 times x minus a, plus 3c3 times x minus a squared, so forth and so on. And if we evaluate that at a, all of these terms go to 0 except for c1. So we get c1 there. And we look at the second derivative. We get 2c2 plus 3 times 2 times c3 x minus a, blah, blah, blah. All of these terms go to 0, and we get left with 2c2. And we take the third derivative. We get 3 times 2 c3 plus 4 times 3 times 2 c4 times x minus a, and so forth and so on. And so when I plug in a, everything goes to 0 except for the 3 times 2 c3. And the fourth derivative, same thing happens. We get 4 times 3 times 2 times c4 plus blah, 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 blah. And when we plug in a, we get the fourth derivative at a is 4 times 3 times 2 times c4. So we might notice a pattern here, all right? I look at this, I'll start with this third one. We divide out the 2 and we get c2 is f double prime at a divided by 2. And c3 is f triple prime evaluated at a divided by 3 times 2. And c4 is the fourth derivative evaluated at a divided by 4 times 3 times 2. So if we think about it, we can really write c1 as f prime of a divided by 1. And c naught as f of a divided by 1 as well. But these things here, 4 times 3 times 2 times 1, and 3 times 2 times 1, and 2 times 1, these all look like factorials. And in fact, they are. So we can write this as the coefficient sub n is the nth derivative of a divided by n factorial. It works for these first two terms because 0 factorial is 1, and so is 1 factorial. So now we've got a general form for this coefficient, and this is going to allow us to define a very powerful tool called the Taylor series. So the power series of the form t sub f of x is equal to the sum from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times x minus a to the nth power, which is expanded to f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus ... is called the Taylor series of f at a. Now, we often deal with a simpler case of the Taylor series where a is equal to 0. And for that special case, when a is equal to 0, the power series of the form m sub f of x is the sum from n equals 0 to infinity of the nth derivative f at 0 divided by n factorial times x to the nth power, which expanded looks like this, is called the Maclaurin series of f at a. So both of these are just named for mathematicians that studied them heavily. So after the Taylor series was discovered, Maclaurin did a lot of research into this special case, and so he got credit for the naming of this special case. Now, really, really important fact here that's not trivial is that not all functions are equal to their power series. So here we said, well, if a function was equal to its power series, then its coefficients look like this. But just because you use coefficients like this does not mean that the polynomial you get will actually be equal to the function. Now, it often will be, and in all of the cases that we really care about for applications, at least for this course, it will be. But there are certain cases where you can find the Taylor series for the function, you find the Taylor series of this form, and it doesn't actually end up being equal to the function. So we have to be a little bit careful, and that means that we have to use some rigor in actually proving that functions are equal to their Taylor series, which we'll get to a little bit later in the video. Okay, so let's start by finding the Maclaurin series of e to the x. So the Maclaurin series for e to the x is the sum from n equals 0 to infinity of the nth derivative of the function e to the x at 0 divided by n factorial times x to the nth power. So first of all, what's the nth derivative of e to the x? It's just e to the x. You take the first derivative of e to the x, c to the x. Second derivative, still e to the x. So the nth derivative is always e to the x. And that tells us that the nth derivative evaluated at 0 is e to the 0, which is 1. And so this series is just the sum from n equals 0 to infinity of 1 times x to the n over n factorial. And this sum expands like this, 1 plus x, so 1 over 0 factorial, which is 1, plus x over 1 factorial, which is still x, plus x squared over 2 factorial, which is really just 2, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, so forth and so on. Okay, so let's just take a look here at some pictures of this function. So first of all, spoiler alert, e to the x is equal to its Taylor series. We still need to show this, and that's going to require some more complicated tools. But let's see what this Maclaurin series is telling us graphically. So we've got the sum and e to the x. So if we took the partial sum, the 0th term, we get 1. We take the first 2 terms, which is s1, because we're starting with n equals 0. It's 1 plus x. s2, 1 plus x squared over 2. s3 is 1 plus x squared over 2 plus x cubed over 6. And so here we've got these things graphed. First we've got y equals 1 graphed. And that takes the same value at 0, when x is 0, as e to the x. And then we take s1, that's 1 plus x. Well, that's the tangent line approximation at 0. And then we take s2. So we look down here. So we divided this into 2 pictures. s2 is this blue graph here. And s3 is the black graph. And what do we see? We see that every single time we add another term to that power series, the partial sum, what do we get? we get a closer and closer approximation. So I want to see that in a little bit more detail here. So we're going to pull up a little graphing tool here. And so this green graph here is just the graph for e to the x. Now what I've done up here, and you can ignore the stuff at the bottom, that's going to come up in a later problem. But what I've done here is set up the sum of x to the n over n factorial. And I'm summing from the 0th term to the a term. So right now, I've got just the 0th term, and I'm going to click that on, and that's that red line. And now I add a term to the sum, and I add another term, and I add another term, and another term, and so forth and so on. And so I'm going to zoom out a bit. And what do we see? The more terms I add, the further the accuracy improves, and the further out that accuracy improves. So, for example, I would say that now between -11 and, let's say, probably pretty far to the right, it's hard to tell without zooming out crazy far, but at least out to like 5 or 6, we've got really good accuracy. And to illustrate how good that accuracy is, I'm going to just zoom in on these two graphs here. And they don't even look like two graphs, right? They look like one graph. Here, I'll turn off the red one. The green one's still there. They're just perfectly overlapped. And I'm zooming in, and I'm zooming in, and I'm zooming in. I mean, we're in thousandths place, 10,000ths place. I would basically have to zoom in for a very, very, very long time to see any meaningful difference in the value of these. Now, if I pull this back, once I have 11 terms, I see some deviation, 12 terms, but hey, look, just at 12 terms, if we look at the vertical distance between these two functions, that's really not that much. If I go out to, say, 15 terms, 14 terms, 13 terms, yeah, 13 terms, very little difference between these functions. So, point being, I don't need that many terms of the polynomial to get really good accuracy for these functions, at least near to their centers. And that's a big important part of this idea. This Maclaurin series is centered at 0. We took the derivatives, we found our polynomials, we centered them at 0. And so the approximation is always going to be best on some interval around 0. But as we add more terms, we get to widen that interval out and get better accuracy over a larger distance. So the reason we care about both Maclaurin series and Taylor series is because Taylor series more generally will let us move the approximation and take that approximation at some other x value. But we'll deal with that in a bit. Okay, so moving on, now we're going to find the radius of convergence for the sum from n equals 0 to infinity of x to the n over n factorial. And we use the ratio test. It's absolute value of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. And I'm just going to kind of skip the simplification here and go straight to the absolute value of x over n plus 1. Which is the absolute value of x divided by n plus 1. And then I'm going to take that limit. So we've done quite a few of these, so just going a little bit quickly there. That limit is 0, so this whole thing is 0. And this implies the series converges for all x. By the ratio test. So what have we shown so far? We've shown that the Maclaurin series for e to the x is this. We've shown that the series converges for all x values. We're missing one piece of the puzzle, which is actually showing that it's equal. to e to the x for all values. So we're going to address that one a little later. But first, fact, the limit as n goes to infinity of x to the n over n factorial is 0 for any real number. And the reason I know that is because this series converges by the ratio test. So remember, we have a theorem that says that if the sum of a sub n converges, that implies that the terms went to 0. And so since we know that the sum of x sub n over n factorial converges, we also know the limit as n goes to infinity of x to the n over n factorial converges. And while we're here, I'm just going to address that this also implies that the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial also goes to 0. Starting at one higher number doesn't change where the numbers approach. It just starts you at a higher point in the list of terms. So we still get the same limit, and that's going to come up later on in this one. All right, moving on. Okay, so now we get to the most challenging part of this topic, in my view, but it is really, really crucial in terms of understanding why we can use these tools. So this is Taylor's formula and Taylor's remainder theorem. So if f of x is equal to the nth degree Taylor polynomial, so here, what this means is the nth partial sum for the Taylor series. And this is what's left over in the approximation. How far off the approximation is. Well, why is that the leftover? Because if I just subtract t sub n across, we get f of x minus the Taylor polynomial is r sub n of x. So literally, r sub n of x means the difference between the actual function and the Taylor polynomial. So t sub n of x is the nth degree Taylor polynomial of f at a, and the limit as n goes to infinity of r sub n of x is 0. Okay, so let me restate this thing. I kind of started in the middle of a sentence that time, and it doesn't quite sound right. If f of x is the sum of the nth partial sum of the Taylor series with the error r sub n of x, and r sub n of x has the limit 0 for all such x, such that x minus a's absolute value is less than r, then f of x is equal to the sum of its Taylor series on that interval. Now this particular theorem is actually pretty obvious, because by definition, the nth partial, the limit of the nth partial sum of the Taylor series is the Taylor series. All right, those are the same thing. So what we're saying here is that if f of x looks like this, and r sub n of x is approaching 0, that tells me that t sub n of x must be approaching f. Because it's got to fill in the gap, right? If these things are equal, and this second term is going to 0, then those partial sums must be approaching f. Now that's all fine and dandy if we know how to find r sub n of x. Now that's where Taylor's formula comes into play. So Taylor's formula: if f has n plus 1 derivatives on an interval I that contains a, which is where we centered our power series, then for any x in that interval I, there exists a z strictly between x and a, such that the remainder term in the Taylor series of f can be expressed as r sub n of x equals the n plus 1th derivative evaluated at z divided by n plus 1 factorial times x minus a to the n plus 1th power. So I want to be very clear about what this says. Taylor's formula shows us that there is a z, but it doesn't tell us how to find it. We don't actually know, in general, how to find the z that works here, but that's going to be okay. We're not going to be too worried about that. Okay, so real quick, just a little addendum, another clarification here. It says that the z is strictly between x and a. So you've centered your Taylor series at some a, and you're trying to evaluate it at some x. This theorem says that this z has to be somewhere between those two things. So that's basically all we get. We get this formula, and we get that z is somewhere between the center of the power series and the point you're trying to evaluate it at. Okay, so now let's take a look at the proof. This proof is pretty tricky, probably one of the most challenging proofs in the course, if I'm being honest. And to be clear, I would not expect students to reproduce this proof. I simply want to make sure that students see this isn't magic, this formula doesn't come out of nowhere, that it actually has some logical, coherent meaning to it. So let the remainder be f of x minus t sub n of x. Now we will cleverly define a constructed function of t. So we will be considering that x is treated as a constant that's not equal to a. So this function is a function of t. We're calling it g of t. And you can kind of think g of t as being f of x minus the Taylor series centered at t, the nth derivative Taylor series centered at t. So what we're changing in this function, this g of t, is actually the center of the Taylor series. So we're subtracting f of x minus that Taylor series, that partial Taylor sum. And then we're also subtracting this remainder expression here, r sub n of x times x minus t to the n plus 1 over x minus a to the n plus 1 power. And that thing's kind of its own thing. Okay, so this cleverly constructed function has a nice property here. And the property that it has is that g of x is 0 and g of a is also 0. So we can see that by just plugging in. If I plug in 0 in place of t, all of these terms to the right here are going to be 0. And then we get f of x minus, or sorry, I said x instead of t. If we plug in x in place of t, all of these terms will be 0, except f of x minus f of t becomes f of x minus f of x, so that's also 0. And if I plug in a, we get f of x minus all of this stuff evaluated at a, which is just the regular Taylor series centered at a, and the regular remainder formula. And then, of course, the sum of these two things is f, so we get f of x minus f of x, which is 0. So that means we can apply Rolle's theorem because we have 2 points, a and x, where the function g of t here is 0 at both points. And so Rolle's theorem tells us that there is a z, and that z is in the interval from a to x, such that the derivative at z is 0. So let's take a look at the derivative for g prime of t. So g prime of t, when I take this derivative, notice that these expressions up here, like f prime of t times x minus t, that's a product rule, and this is a product rule. and a product rule. All of those terms are going to require product rule derivatives. And so I'm not going to go through every one of those individually, but this expression here is what we get when we take all of those product rule derivatives. So negative f prime of t minus f double prime of t times x minus t plus f prime of t minus f triple prime of t over 2 factorial, yada, yada, yada. So you get this expansion for the derivative, and then you get a bunch of stuff that cancels. You get like the negative f of prime of t cancels this, and then the second derivative here, it gets canceled with this, and so forth and so on. And a bunch of stuff cancels. And in the end, what actually gets left in your expression is negative the n plus 1th derivative of f at t divided by n factorial times x minus t to the nth plus n plus 1 times r sub n of x times x minus t to the nth over x minus a to the n plus 1th power. Of course, we plug in z because this thing is at z is going to be equal to 0. And then we do a little bit of algebra to rearrange and solve for r sub n of x. So you can go through, look at those steps carefully, see how it's rearranged. But the result is that we get r sub n of x is the n plus 1th derivative at z divided by n plus 1 factorial times x minus a to the n plus 1 power. Okay. So again, pretty tricky proof. I would never expect a student to reproduce this on their own. Some people got famous writing proofs. A lot of people have gotten famous writing proofs like this for good reason. So that's totally fine, but I did want to make sure you saw where this comes from, that this isn't magic. Okay, now we're going to use it to prove that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. So we've sort of done two pieces of the puzzle here. We found the Maclaurin series, and we showed that it was convergent. So we already showed that the Maclaurin series, I should write m. We already showed that the Maclaurin series for this function is this sum. And we showed that this series converges everywhere. And now we're going to show that it's actually equal to the value of e to the x. So how do we show that it's equal to the value of e to the x? Well, we go back to that theorem. That theorem says if the remainder has a limit of 0, then f of x is equal to the sum of its Taylor series on the interval of convergence. So we just have to figure out how to show the limit of the remainder is equal to 0. That's not trivial, by the way, but that's what we're trying to do. So the first thing I have to do is write out my remainder formula. And really, I only need that the absolute value of the remainder goes to 0. I should maybe be more precise about that. So we're looking at the absolute value of r sub n of x. And our formula for that is the absolute value of the n plus 1th derivative at z over n plus 1 factorial times x minus a, but a in this case is 0 because it's the Maclaurin series, so that's x to the n plus 1th power. And the great thing is we already know that the n plus 1th derivative for e to the x is still just e to the x. So that tells me that the n plus 1th derivative evaluated at z is just e to the z. So now I want to show that the limit of this thing goes to 0. But I have a little bit of a problem, a technicality here. And the technicality is that z, so this is kind of your warning, warning, z depends on n. So which Taylor polynomial you are taking will decide what the value of z is in the remainder formula. So what degree you're using changes z. That means that when we take the limit, so when I try to take the limit of this expression, we'll just write this off to the side here. The limit as n goes to infinity of e to the z x to the n plus 1 over n plus 1 factorial. When I try to take this limit, I have a real problem here because I can't pull e to the z out of the limit because it depends on the value of n. So it's not treated as a constant. So in other words, not a constant value. So that means we have to come up with some clever way to get that e to the z out of the way of our limit. So the way we're going to do that is just break into two cases. X being greater than or equal to 0. And I mean, we could do x equals 0 separately. We'll just do x greater than 0. And if we look at that case, so here's 0, here's x. That means z is between 0 and x. And if z is between 0 and x, that tells me that e to the z is smaller than e to the x because exponential functions are increasing. Bigger inputs give you bigger outputs. So what does that tell me? That tells me that my remainder expression, e to the z times x to the n plus 1 over n plus 1 factorial, is bounded by e to the x times x to the n plus 1 over n plus 1 factorial. And it's also bounded by e to the 0, which just gives me x to the n plus 1 over n plus 1 factorial. So now, what do I know? I know, so we already showed that the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial is 0. But that implies that the limit as n goes to infinity of e to the x times x to the n plus 1 over n plus 1 factorial is e to the x times this limit. And that is also 0, because note, x doesn't depend on n. So when I look at this upper bound and I've bounded this by e to the x, that thing is treated as a constant in terms of this limit. So I've got the limit of this left side of the inequality and the right side of the inequality are both 0, and that implies that the limit as n goes to infinity of e to the z times x to the n plus 1 over n plus 1 factorial is 0 by the squeeze theorem. And so now I'm going to look at the case when x is less than 0. So if I draw my little number line here, here's 0, here's x, that puts z in between them, but that means then that e to the z is bigger than e to the x. So my inequality changes. It looks like e to the z times x to the n plus 1 over n plus 1 factorial is bigger than x to the n plus 1 over n plus 1 factorial, which is less than e. That should be e to the x there. And then on the right-hand side, we just have x to the n plus 1 over n plus 1 factorial. So in essence, it works out to where we have the exact same limits in play here. It just changes the inequality, so it would mess up our squeeze theorem argument a little bit. So this does still imply that the limit as n goes to infinity of e to the z times x to the n plus 1 over n plus 1 factorial is 0 by the squeeze theorem. And of course, I split it into x greater than 0 and x less than 0. If x was equal to 0, that's trivial because all the terms will be 0. So it obviously, you're going to get the same thing as e to the 0, all the terms except for 1. Okay, so with that, this gives us our conclusion. The remainder is 0, which implies that the Taylor series equals e to the x. I should say the Maclaurin series. It is a Taylor series at 0, but the Maclaurin series is equal to e to the x. And what that really means is that, hey, we can feel comfortable knowing that the Maclaurin series that we're using here, that we can actually use them to solve problems, and they are going to represent accurate values for the function, right? That's why this is important. It's difficult, but it's important to know that these functions, that these Maclaurin series actually work, that they do what we think that they do. All right, so let's move on. So now we got a big one. So now we're going to do all 3 things that we talked about before, but all at once. So find the Maclaurin series for sine of x and prove that it's equal to sine of x for all x. So this requires first finding the series, then showing that it converges and where it converges, then using Taylor's remainder formula to prove that it actually is, the limit is actually equal to the original function. So now for e to the x, it was actually pretty trivial to do this. With most functions, it's a little trickier, and we need a little bit more pattern recognition in order to figure it out. So with that in mind, we're going to try to set up a table to keep track of our information here. So keep in mind, this is a Maclaurin series, so we're talking about a being equal to 0 here. And so if a is 0, we're going to set up a table with our values for n, the nth derivative of f at x, and then we're going to evaluate that nth derivative at a, in this case 0. So we're looking at n is 0, 1, 2, 3, 4, 5, 6, and that's enough. If we don't recognize the pattern by then, we've got a problem. So sine of x, cosine of x. So the 0th derivative is sine of x. The first derivative is cosine. Second derivative is negative sine of x. That makes the third derivative negative cosine of x, which makes the fourth derivative sine of x. And then cosine of x and negative sine of x repeat. Now if I evaluate those derivatives at 0, sine of 0 is 0, cosine of 0 is 1, sine of 0 is 0, negative cosine of 0 is negative 1, 0, 1, 0, negative 1, so forth and so on. So now when I go to write out my Maclaurin series, I can write it all out like this. 0 times x to the 0 power over 0 factorial plus 1 times x to the first power over 1 factorial. Keep in mind, these are my coefficients for each term, right? That's what we've got here. So plus 0 times x squared over 2 factorial plus negative 1 times x cubed over 3 factorial plus 0 times x to the 4th over 4 factorial plus 1 times x to the 5th over 5 factorial plus ... That's enough. Now let's clean up this expression a little bit. This is 0, so I just get x over 1 factorial plus 0 minus x cubed over 3 factorial plus 0 plus x to the 5th over 5 factorial plus ... So notice in our regular Maclaurin series notation, each value of n would correspond to each power of x. But because half of these powers disappear, we're going to have to figure out a different way to express our power series. And how are we going to do that? Well, we're still going to write it from n equals 0 to infinity. But since the terms are alternating between positive and negative, we'll have a negative 1 to the nth power here. When I plug in n equals 0, I get a positive 1, which is exactly what I want, times x to a power. Now, this is the tricky part. If I look at just the power here, I'm going up by 2 each step if I'm just looking at the power. And so that tells me my power should be 2 times a multiple of n. Except that it's got to be an odd number. It has to start at 1, so I can just tack on an extra 1 there. Plug in n equals 0, you get 2 times 0, 0 plus 1, which is exactly what I want. Now I notice my factorial is always the same as my power, so I can use the same expression, 2n plus 1 factorial there. And there, that's our Maclaurin series for sine of x. So this is part 1. Find the Maclaurin series. Now part 2 is show it converges. Meaning that you get values for the series everywhere. So we do our ratio test like normal. We've done a bajillion of these at this point, so the absolute value of a sub n plus 1 over a sub n looks like negative 1 to the n plus 1 times x to the 2 times n plus 1 over 2 times n plus 1 factorial. And instead of dividing by the other term, I'm going to just jump straight to multiplying by the reciprocal, which will give me 2n plus 1 factorial over negative 1 to the n times x to the 2n plus 1. And then we'll rewrite this a little bit. Negative 1 to the n plus 1 over negative 1 to the nth power leaves us with just a single factor of negative 1. And here we've got x to the 2n plus 2 plus 1. It's x to the 2n plus 3 times 2n plus 1 factorial over, this will be 2n plus 2 plus 1, that's 2n plus 3 factorial, and then this term is x to the 2n plus 1. Now I'll simplify a little bit further. When I take the absolute value, that negative is going to disappear, so I'll just disappear it now. X to the 2n plus 3 over x to the 2n plus 1. I subtract my exponents, leaves me with x squared times. This is 2n plus 1 factorial over, and the 2n plus 3 factorial we can expand to 2n plus 3 times 2n plus 2 times 2n plus 1, so forth and so on. So this will be a factorial, and those cancel. And so now I'm going to jump straight into taking the limit. So we take the limit of our ratio here. That becomes the limit of x squared over 2n plus 3 times 2n plus 2. And x squared is treated as a constant here, so obviously our denominator is going to infinity, so the whole thing is going to 0. So this implies that the series converges for all x. And so part 3, the last part here is that we need to show that the Maclaurin series is actually equal to sine of x. In other words, show that the limit of the remainder goes to 0. Okay. Whew. What can we do here? Well, when we look at the absolute value of r sub n of x, that's the absolute value of the n plus 1th derivative at z times x to the n plus 1th power over n plus 1 factorial. So let's do a little aside here. This is kind of the critical thing. When I look at this n plus 1th derivative, it's got to be cosine of z, or negative sine of z, or negative cosine of z, or positive sine of z. Any derivative I take, no matter how many terms I go down, any derivative of this sine of x is going to be one of those four things. And what does that tell me? That tells me that the magnitude, or the derivative, the n plus 1 derivative, its magnitude is always less than 1, because sine and cosine have maximum values of 1, and making them negative doesn't change the magnitude, the size of their maximum values. So this thing is bounded by 1, and that tells us that our remainder formula here, our absolute value of our remainder formula, is bounded by the absolute value of x to the n plus 1 over n plus 1 factorial. And since the limit, and obviously this is magnitude, so it's greater than or equal to 0, and since the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial is 0, that implies that the limit of our remainder is 0 by the squeeze theorem. So this case is a lot easier, in my opinion, than the e to the x case. And I should add to the end here, finally, the Maclaurin series is actually equal to sine of x, right? The series we found is the same as sine of x. Okay, so that's a pretty challenging problem. Let's do something a little simpler. Now, it seems like it'd be just as difficult. Find the Maclaurin series for cosine of x, but we can use the knowledge that we already have. So since cosine of x is the derivative of sine of x, we can take the fact that sine of x equals the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, and take its derivative, and that implies that cosine of x is the derivative of this series. And the great thing here is we know that the derivatives of power series have the same radius of convergence as the original power series, and since the radius of convergence for sine is infinity, we also know that cosine will converge everywhere. So this implies that cosine of x is equal to the sum from n equals 0 to infinity of negative 1 to the n times 2n plus 1 times x to the 2n, I just subtracted 1 from my power, multiplied by the original power, divided by 2n factorial, but I'm going to, or 2n plus 1 factorial, but I'm going to rewrite that as 2n plus 1 times 2n factorial. So these cancel, and that leaves me with the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 2n over 2n factorial. Now notice I didn't change my lower bound on my sum, and that's because the first term in the series for sine is x to the first power. It's not a constant, so we keep that n equals 0 for our lower bound. Okay, now example 6, find the Maclaurin series for f of x equals 1 plus x to the k power, where k is any real number. We call this series the binomial series. Okay, so I'm going to make that same chart that I made before. We'll take n, we'll take the nth derivative of x, And then we'll plug in 0 for our Maclaurin series. So for n, we start at 0, 1, 2, 3, 4, etc. That's enough. And our original function is just 1 plus x to the k. So its derivative is k times 1 plus x to the k minus 1. And so the second derivative is k times k minus 1 times 1 plus x to the k minus 2. And so forth and so on. K times k minus 1 times k minus 2 times 1 plus x to the k minus 3. Didn't really give myself enough room there, so let me just move this over a little bit. And we'll just stop at that third term because that's honestly going to be enough to understand the pattern here. And when we evaluate this derivative at 0, we get 1 for the first term. We get k times 1, so that's k. And then we get k times k minus 1. And then we get k times k minus 1 times k minus 2, so forth and so on. So when we long form write out our Maclaurin series, we get 1 times x to the 0 over 0 factorial plus k times x to the first power over 1 factorial plus k times k minus 1 times x squared over 2 factorial plus k times k minus 1 times k minus 2 times x cubed over 3 factorial plus so forth and so on. And now, how can I write this in series form? Well, the way we denote this in series form is as follows. I write the sum from n equals 0 to infinity of k choose n times x to the n. So this symbol here that looks like a bracket with k stacked over n is read k choose n, and it's read that way because the formula that it's describing is a formula from probability or statistics about choosing a certain number of objects from another pile of a certain number of objects. So like you might say, there are 10 objects, choose 3. So the formulas for those probability expressions work out exactly the same. However, in this context, we're not talking about probability. It just happens to be the same formulas, so we use the same terminology. The difference here being in probability, k and n have to be whole numbers, but k here can be any number in this context. It can even be negative numbers. So we say this is the sum from n equals 0 to infinity of k choose n times n to the n, x to the nth power, where k choose n is given by the formula k times k minus 1 dot 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 times k minus n minus 1, all divided by n factorial. So this is a little tricky. K here looks like k minus 0. So notice, what have we got here? N terms. That's the basic idea. Okay, so that's our Maclaurin series for the binomial series. And let's move on. Or maybe I should have said more clearly, like this is the nth term. Just trying to think about how to best say that, right? So when I look as third term, this is always 1 less than that. Second term, 1 less than that. Okay, hopefully that's clear. So anyways, moving on to our last example. Find the Taylor series for sine of x at a equals pi over 2. So up to this point in this section, we did focus entirely on Maclaurin series rather than Taylor series. There's really no difference between the two meaningfully, except that the Taylor series can be centered anywhere, so you might have to plug in different a values. So we're just going to do one example of that. And I'm still going to set up the exact same type of chart here. Zero, 1, 2, 3, 4, 5. Blah, blah, blah. We're just looking for the pattern. 0th derivative is still sine of x. First derivative is cosine of x. Second derivative is negative sine, negative cosine, positive sine, positive cosine, so forth and so on. But now I'm plugging in pi over 2 instead of 0. So sine of pi over 2 is 1, and cosine of pi over 2 is 0. And negative sine will be negative 1, and then 0, and 1, and 0, and so forth and so on. So now this Taylor series is going to look like 1 times x to the 0, x minus pi over 2, right? It should be x minus a, x minus pi over 2 to the 0 power over 0 factorial. Plus 0 times x minus pi over 2 to the first power over 1 factorial. Minus 1 times x minus pi over 2 to the second power over 2 factorial. Plus 0 times x minus pi over 2 to the third power over 3 factorial. Plus x minus pi over 2 to the fourth power over 4 factorial. And that's plenty. So I'll simplify this expression. The first term, the 0th power and 0 factorial are both 1. So 1 times 1 is 1. Second term disappears, and we get minus x minus pi over 2 squared over 2 factorial. Plus, and the next term will be this fourth power term. So that's x minus pi over 2 to the fourth power over 4 factorial. Minus dot dot dot. So now we look for a general formula in the same way that we did before. N equals 0 to infinity. And I can express this as an alternating series, negative 1 to the nth power. But the only difference between this and what I did for sine before, centered at 0, is that all of my powers are even now. So this is 2 to the n over 2n factorial. And you can always double check when n is 0, what do I get? I do still get 1 for my 0th term. So this is equal to sine of x centered at a is pi over 2. And so let me just wrap up this video by pulling back up this graph we were looking at earlier. But now, instead of looking at e to the x, let me try to zoom back at here. Will that do a quicker version? There we go. All right, great. So this is our approximation for e to the x, and e to the x was centered at 0. So you see, all the approximations take this exact value at 0. But now, let's get off of the approximation for e to the x, and let's look at the graph for sine of x. And so now, what I'm going to look at is the partial sums for the Taylor series at pi over 2 that we just found. So now, since we're centered at pi over 2, notice when we look at the 0th sum, we get that straight line passing through at pi over 2. And then 2 terms, I get that. And now we'll zoom out a bit. So we're centered at pi over 2 here. And then our approximation as we add more terms, see here's the terms being laid out. Wrong terms, these terms being laid out. That's for the other problem. But as we add more terms to our sum, what happens to our approximation? Its accuracy increases, and where it's accurate stretches out in each direction. Okay, so that's it for this video. Thank you for watching.